We are going to learn how to use implicit differentiation to find partial derivatives. There are two theorems we will need to find the derivatives of implicitly defined variables. Let's start by looking at a function of two variables. If y is defined implicitly as a function of x by the equation f of x y equals 0, then the derivative of y with respect to x is equal to negative 1 times the partial derivative of f with respect to x over the partial derivative of f with respect to y, as long as the partial derivative of f with respect to y is not equal to 0. Similarly, if we have z defined implicitly by the equation f of x y z equals 0 as a function that is differentiable for both of x and y, then the derivative of z with respect to x is negative 1 times the partial derivative of f with respect to x divided by the partial derivative of f with respect to z. The derivative of z with respect to y is negative 1 times the partial derivative of f with respect to y divided by the partial derivative of f with respect to z. Note that both of these derivatives will only be defined if the partial derivative of the function with respect to z is not equal to 0. Let's look at an example and find the derivative of y with respect to x of f of xy if this is f of xy. To find the derivative, we need to find the partial derivatives of the function with respect to x and with respect to y and substitute them into this equation. Let's start with fx. The derivative of 6 squared is 12x, minus 3xy is minus 3y, and plus sine xy squared is plus y squared cosine xy squared. Now find fy. Notice that the first term doesn't have a y component, so the partial derivative with respect to y is negative 3x plus 2xy cosine xy squared. So the derivative of y with respect to x is negative 12x minus 3y plus y squared cosine xy squared over negative 3x plus 2xy cosine xy squared. Now let's find the derivative of z with respect to x and with respect to y when z is defined implicitly and f of xyz is differentiable with respect to x, y, and z. Remember, dz dx is equal to negative 1 times the fx over fy. Starting with the partial of f with respect to x, we find fx is 5 sine squared quantity 7z y to the fourth x to the fourth plus 3ye to the z. Likewise, we find that fz is 7 sine quantity 14z y to the fourth x to the fifth plus 3xye to the z. Substituting both of these partial derivatives into the equation for dz dx, we see that the derivative of z with respect to x is the opposite of 5 sine squared quantity 7z, y to the fourth x to the fourth plus 3ye to the z all over 7 sine quantity 14z, y to the fourth x to the fifth plus 3xye to the z. Using the same methodology, we find dz dy using the partial derivatives of the function with respect to y and z. We already found the partial of f with respect to z, so we need to find the partial of f with respect to y. Looking at the given function, we see that the partial derivative with respect to y is 4 sine squared quantity 7z, y to the third, x to the fifth, plus 3xe to the z. Plugging this into the equation from the theorem, we find that dz dy is the opposite of 4 sine squared quantity 7z, y to the third, x to the fifth, plus 3xe to the z, all over 7 sine quantity 14z, y to the fourth, x to the fifth, plus 3xye to the z.